one, number systems and the number line. So we have 5 sets of numbers that make up our grand set of real numbers. Okay, how many number systems do you know from last couple years? One's place value for a number line, or for, okay, that's place value, guys. What kinds of numbers do we have? What are positive and negative numbers called? Integers. So integers are one kind of number. What are the kinds of numbers do we have?
Decimals.
Okay, decimals are found in a set of numbers. Fractions are also found in a set of numbers. Product, multiplying and dividing. We're looking at for a set of numbers. Percentages, set of numbers. Okay, here we go. The first kind of numbers we have are called our counting numbers. Our counting numbers are called the natural numbers. So N for natural numbers. Okay, now the natural numbers, like I said, their other name is called the counting numbers. Now, what do we know about counting numbers? What number do we start counting at? 1. Good. So this number system, this group of numbers only has the numbers 1 to positive infinity. So these are numbers 1 all the way to positive infinity. A sideways kicked over 8 is the infinity symbol. Okay, 1 to positive infinity.
Why is it positive?
Okay, the next set of numbers. What number system only adds the number 0 to the natural numbers? Do you remember what that was called? Starts with W. Whole numbers. Okay, it starts with a W. The second system is called W for whole, so whole numbers. Now, whole numbers are all of the natural counting numbers plus 0. They include 0. Okay, so 0 all the way to positive infinity. So no negative numbers yet. On my number line, I'm only on the positive numbers and 0 right now. Okay?
What's that symbol right there?
That's a number sign.
No.
The hashtag is a number sign. It's an S for numbers. It's an S. No problem. Okay. Now we have the next set of numbers from our number line. What other set of numbers do I have after I include 0 on the number line? I have my negative numbers on the other side of the number line. So those are called integers. Yes, well done. So you're going to go from negative infinity. Whoa. Where's that going? There we go. So we're going to go from negative infinity to positive infinity. So any negative numbers and any positive numbers and 0 on the number line. Have we seen fractions and decimals and square roots yet? No, they haven't come up yet. They're not in these number systems. Okay? So when I want to put fractions and decimals and square roots, they're in my next set of numbers. My next set of numbers is called rational numbers. Okay? And ironically, it's a strange symbol. The symbol is a Q. So for rational numbers, that's set 4, is a Q. Now how come? Q stands for quotient. Okay? Now I'll explain what that means in a moment. So this is our rational numbers. Okay, rational numbers. Now rational numbers, these ones include fractions, perfect squares, okay, now remember, fractions are written in this form, A over B. But remember, B cannot be 0 because you cannot have a 0 on the bottom of any fraction. So whenever you've got a fraction in generic form, you've always got to put A over B, but B can't be 0. Your bottom can never be 0. So A is the top, B is the bottom. Now, that's fractions. Since I can put it into fraction, what does that fraction line mean? Divide. Now, what is the answer of dividing? It's called quotient. That's where the Q comes from. Okay, so rational numbers can all be put into fraction form. So that's where the letter Q comes from. It stands for rational. Okay? Now the other set of numbers, there's only one last set of numbers, and that's called irrational. So basically not rational. So if it's not rational, we have a symbol that means not rational. Not rational is the Q with a negative sign on top. The negative sign on top means not rational. Okay? So that's why they're called irrational. Okay, so Q with a negative sign, that's irrational numbers. Now in these ones, the biggest thing is these ones cannot be put into fraction form. Okay, so these numbers can't be put into fraction form. Fraction form meaning A over B. They can't be put into fractions. Now why? The reason is all of these numbers, there's only two kinds of numbers here. Well, actually only one kind of number. The other one creates it. The only kind of number that exists in this category are run-on decimals. Okay, run-on decimals with no pattern. Okay, with no pattern. Now, where do we find other decimals that have patterns and repeating decimals and ending decimals, terminating decimals? The other decimals go up here in the rationals. So the other decimals go up here with those fractions. I can also have decimals up there. Okay?
So a good way to not perfect decimals, but
Any decimal. So what we say is that decimals can be rational unless they're run-on decimals. Run-on decimals are never rational. How come? Because a run-on decimal number, you have to round it because it never ends. And because it never ends, you have to be able to have a number that ends to put into fraction form. So if a number never ends, it can't be put into a fraction. And that's why run-on decimals are the answer for this one. Now, what kinds of numbers give you run-on decimals? Non-perfect square roots we figured out from last chapter. Okay, from our last unit, we found out that perfect squares had decimals that end or repeat, and we found out that non-perfect squares are decimals that run on forever and they do not have a pattern. So these guys are non-perfect square roots. Okay, so non-perfect squares go there. Okay. Now let's go back up to the top here on rationals. There's two kinds of decimals that we can have. Okay, there's two kinds of decimals that we can have in rationals. One is called repeating decimals. Okay, repeating decimals with a pattern. Okay, and the other kind of decimal is called terminating, which means they stop or end. Okay, so terminating. Okay, those are the kind of decimals that are allowed to happen in the rational one. In the irrational one, we don't see those kinds of decimals. We only see run-on decimals with no patterns. Okay, so there's three different kinds of decimal numbers: run-ons with no pattern, repeating with a pattern, or ending. Okay, so those are the kinds of decimals we deal with. The irrationals can't be put into fraction form, and they're the run-on ones. They're the non-perfect squares. So in the rationals, I would find root 4. That gives me an answer. Root 0.36. That gives me an answer, same as root 4, as an exact decimal answer. Okay? If on the bottom here I go down into the irrationals, non-perfect squares, if I go root 7 and you type root 7 into your calculator, it's going to fill your entire calculator screen. How come? Because it's a run-on decimal. Okay? The last number of your calculators, the calculator automatically rounds it. Okay? So it looks like it ends because the calculator rounds it on purpose because it can't keep going on forever on your calculator. So just a few of you have just said, an example of a run-on decimal that never ends, pi. Okay? There's also another one on your calculators. You'll see the letter E. you see the letter E on your calculator? That's also a run-on decimal. If you type in E exponent 1, it's going to give you a run-on decimal, 2.718, and it goes on forever. Pi is 3.14 and goes on forever. Okay, those are two common run-on decimals. Okay, they're both irrational. An example of this, if you take a look, here is a pattern number. It looks like it's following a pattern. You tell me if this is rational or irrational, okay? I've got 3.44444, and so on. Those three dots mean and so on, meaning it continues forever. Would that number be rational or irrational?
Rational.
Rational, good, because it shows a pattern. What about this number? What about that one?
Oh, irrational.
Okay. Okay, quiet, quiet. Everybody put your hands up if you think it is rational. Put your hands up if you think it's irrational. Put your hand up if you don't have a clue. Okay. This one looks like it has a pattern because it goes 4 to 5, then 4 to 6, then 4 to 7, then 4 to 8. But it's not the exact same pattern repeating. It has to be the same pattern repeating to be a run-on or to be a repeating decimal. So this one is irrational. Okay? This one is rational. So if you had another number that went like this, 3.456, 456, 456, and so on, that is rational because the 456 repeats.
Yeah.
Okay.
The difference with that one is even if it's just one number changing that number is what messes up the pattern.
It does. It messes up your pattern. Over here we've got 4, 5, then 4, 6. The pattern doesn't stay with the same digits repeating. Okay? It's repeating different numbers in a different pattern. Okay? That's why this number here is irrational. Okay, let's look at the bottom of your page. It says the Frere model. The Frere model is an excellent tool to help you understand keywords and concepts. This is where you're going to take your highlighters and highlight some things here. So it tells us the Frere model consists of a key term in the middle, okay, followed by 4 sections for your definition, characteristics, examples, and non-examples. So we're going to do one for each set of numbers. So let's take our very first set of numbers. Okay, as we see here, this is where we're going to take our highlighters and highlight the information. So right now we're talking about the natural number system. And what we wrote down before, these are our counting numbers. So you might want to add the phrase counting numbers. Okay, now what is the definition? The set of numbers that are greater than or equal to 1. Okay, they're bigger than or equal to 1. No fractions, no decimals. So we have no fractions. We have no decimals. No square roots. Okay? And we have no negative numbers. We have no negatives in there. And we also don't have 0. We also don't have 0 in that set. So an example are every type of number without fractions or decimals and square roots. 1, 4, 9, 99, 1,000, 24,352, 5 billion, 9 quadrillion. All of those are numbers that are 1 or above. Okay? Numbers that are not, I have a negative here, doesn't belong to this set. 0 doesn't belong to this set. Fractions don't belong here. Decimals don't belong here. Neither do repeating decimals, neither do square roots. None of those belong in this set. Okay? As each set gets bigger, we have a different set of numbers. Okay? And a different amount of numbers. I've got an example here of my boxes. So, my boxes, you're going to notice the smaller box fits into all the bigger boxes and so on. So my smallest box here is my natural box, the natural numbers. Okay? Numbers 1 to infinity. My next set of numbers, my whole numbers, these ones include 0. So if you notice with my boxes, I can put all the natural numbers into the whole number box. They fit. But if you do it the other way, can whole numbers be called natural? No. If you visually look, you do not fit the big box into the small box. There's one extra number in here that has a 0, which means there's too many numbers in this set. So it doesn't fit in the small set. Okay? Let's take a look at the next set. Oh, definition. We weren't finished with this guy. So if we take a look at our definition here, we've got natural numbers and 0. So this guy has our 0 with him. Okay, examples. You can have all the examples from the natural numbers, and they include 0, of course. What will you not find? You're not going to find negatives. You won't find fractions. You don't find square roots. You don't find decimals. Okay? They're not in that category yet. They're too big for this category. Now, the symbol is W. On the number line, they're represented by dots. Okay? An exact dot on the number line. How come? Because it's an exact amount of something. 5, 0, 15. They are exact numbers on the number line. So if I wanted to draw one number line of one example, if I wanted to do an example of 17. Well, 17, if 0 is way over here, 17 could be there. I would put a big black dot on 17. The black dot means that it's exactly 17. It hasn't moved off of that number. It's exactly 17. Okay? Let's take a look at integers. Integers is on the next page. This is the set of natural numbers and their opposites. So all the positives now and the negatives and 0. Okay? So you've got your whole number line now. The negatives, 0, and the positives. All right. Examples you're going to see here, negative numbers. Yes, you can have perfect squares here. Now, why do you see a perfect square in there? We thought the perfect squares only showed up as irrational number. Why do you think it's here? Any guesses? Yeah. Yes, because it's not simplified. You always have to solve them. Well done. So when you see root 25, if it's a perfect square, you must solve that. So it's actually the number 5, and that will disappear. So because of that, its answer is in the integer set. It's actually a natural number, and it's actually a whole number. So I could have put root 25, or all the perfect square roots, I could have put them all in every category so far. How come? Because when you solve a perfect square, the root sign disappears. Okay? And you get a decimal that ends. Okay? This one has a decimal, it's 0.0. Do we have to write it? No. Okay. The stuff that is not examples, the non-perfect squares. So non-perfect squares are here, repeating decimals, ending decimals, and all kinds of fractions. Okay? Let's take a look at the other ones. And again, what is represented by dots? Same thing, it's just a dot on the number line. Okay? So the number 50. The number 50 would have one single dot on the number 50. Let's take a look at rationals. Here's our big category, rationals. Now, here's my orange box. It's rational numbers. If you take a look at rationals, it says they need to be in the form A over B. A over B means they're in fraction form. Okay? That's another way of saying fractions. Okay? Fraction form is this A over B. Now, whenever they give you a fraction form, they have to tell you what the bottom can't be, because you can never divide by 0. If you try to divide by 0 on your calculator, it's going to say error. Okay? It's a syntax error. It won't let you do it. All right. Rational numbers are the ones we're talking about. So in this category, it is almost our hugest set of numbers. It's our biggest box if you look at the boxes. All of the natural numbers fit in there. All of the whole numbers fit in there, and all the integers. Okay? So it's got positives and negatives. It's got fractions. It's got decimals. It's got perfect squares. But what does it not have? It does not have non-perfect roots. It doesn't have pi. It's a run-on decimal. If you're not sure, that's a run-on decimal. Okay? And that's what this is showing us. Whoa.
It says it's not a pi.
Yeah, this is also a run-on decimal. Okay? All right. Well, let's take a look at irrational numbers. Irrational numbers, like we discussed, these are the numbers that are run-on decimals. These cannot be put into A over B, which means they cannot be put into fractions. Okay? So they cannot be put into fraction form. How come? Because they create run-on decimals. And to create a fraction, you need to have an ending decimal or repeating decimal. So you cannot put these numbers into decimal form unless you round them. Okay? So they can't be put into fractions. Yes, they can be put into decimals. They're just rounded or run on. Now, examples, root 15, non-perfect square. Root 16 is the perfect square. Run on decimal. Root 2, again, non-perfect square. And pi, who is our irrational number. We could also put that E. That's E. Ruler's number. Remember we talked about him. He's 2.17 and so on. Non-examples. Where would you not find numbers in this category? Well, this category is actually a pretty small category. It doesn't have a ton of numbers in it. Well, it sort of does. It has all the non-perfect squares. So what won't you find? You won't find a perfect square there. You're not going to find 0. You're not going to find natural numbers. And you're not going to find fractions. You're not going to find any of that. You're not going to find ending decimals. You're not going to find decimals that repeat. You're only finding run-on decimals. And non-perfect squares create run-on decimals. That's why they are. Okay. Let's take a look at how we would draw this. This is called a Venn diagram. Venn diagrams help us sort our information. So how can we sort our information? Yeah, it says Venn diagram, you bet. So any idea of how to fill that in? Where am I going to put all those numbers? Well, I showed you with my boxes. Who is this teeny weeny box in the middle? That's your natural numbers. Put N there, natural numbers in that box. So I've got my baby numbers. Positive 1 to infinity. What is my next category? W, which is whole numbers. Okay. What is my next set of numbers? Integers. We need the negatives and positives first. So integers, letter I. Then my big box is Q, rationals. Okay, so I'm going to use a Q here for rational. All right. What's this side on the right-hand side? It has nothing to do with these boxes. This side here on the right.
All the numbers.
Not all the numbers. The irrational numbers. Okay, so over here we've got this whole box is for the irrationals. Okay, so all the non-perfect squares, okay, all the run-on decimals, they belong in that box. Okay? So the left-hand side, they go together. Can you ever mix these, or will they ever be together? No. But they form all together, all of those 5 sets of numbers. They form one grand big set. And what is the big set called? The real number system. Okay, so my big box I'm showing you here is the real number system, and it contains all my boxes and then a non-box. This is not a box, it's a glue stick. This is my irrational numbers. It doesn't fit with these guys. It's totally different. Okay? So it does not fit with those. All right, let's move on here. Another way you can do it is see how the numbers relate as a flow chart. So this is called the flow chart example. So everything is in the real number system. You can read it from the top or the bottom. Usually I read from the bottom up. So here I've got the real number system, and it's branching out. It's branching out into rationals and irrationals. You could also branch it the other way. You could also do this. The real number system is the capital R. That's where the R stands for. That's why we don't use R for rationals. Then it branches off into 2. Rational and irrational. Then a rational branches off. Rational branches off into integer, then whole, then natural. So you can do it positive or negative. So you could do it reading it up or reading it down, whichever way you like the flowcharts to go. All right. If a number is in one of the categories, it's going to be in all of the other categories. So let's pick the number 7. We pick the number 7. Where do I find that number 7 first? Yeah, natural. So number 7 would go here. But what do you know about all those little boxes? They fit inside each other. So that means 7 is a whole number, and it's an integer, and it's a rational. Okay? So when we try to categorize numbers and see what they are, that's what they become. So if I had a chart, I would check off every box for this one. The only box I wouldn't check off is the irrational box. Because we often see a chart, okay? And sometimes we see a chart that looks like this. And it's going to have our example, and then it's going to have natural, whole, integer, rational, irrational, and it'll also have one at the back for real. So your example, if I have the example 7, 7 would go into everything except the irrationals. Okay? Pi would be irrational and real. Okay? Because they all fit into that grand category. They all still fit into this big box. Okay? So they're part of the same system, but they don't go together. Okay? Yep. So the next example, if I have a 0, 0 is a whole, but it's also an integer, and it's a rational, and it's a real number. Okay? It's not an irrational number. What about the number negative 100? Well, negative 100 is a negative number, which gives me an integer first. If it's an integer, it's also a rational, and it's also a real. Okay? 5.6794 and so on goes on forever. That's a run-on decimal. That would be irrational and real.
So it's basically you figure out what is first and then it has to.
Yes. You figure out what the smallest category it is. It's every category above it except the irrationals. And if it's an irrational number, it's only 2 choices, irrational and real. That's it. Okay, let's take a look at the practice questions and see if we know the answers. So it says, classify the number 5. Okay, well the number 5, first of all, we know that it's natural, then it's a whole, integer, rational, and real. So it gets 4 out of those 5. Or sorry, 5 of the numbers. It gets 5 number sets. The only one it doesn't get is which one? Irrational. Good. The Q with the negative sign. Doesn't get that one. Number 2 says the set of natural numbers is bigger than the set of whole numbers. True or false? Well, if you're not sure, take a look at the size of the boxes that I have here in my example. So it says, is natural bigger than the wholes? No, the whole numbers have 1 extra number. They have 0, so that's false. The next question, what is the only difference between natural and whole? What's the only difference between here?
Zeros.
Whole has 0. Okay? So whole includes 0. Okay, so the whole includes 0. Number 4, the square root of a number is always going to be an irrational number.
False.
False. How come? There are perfect squares, aren't there? Root 4 is 2. Root 16 is 4. Okay, root of 100 is 10. So there are perfect squares. So their answers are not always run-on decimals. So that is false. Because the question here is saying it'll always be. That's false. 5, an irrational number can be put into a fraction. False. That's the one thing it can't do. That's why it's called irrational, because you can't put it into a fraction. The rationals are bigger than the naturals. So the rational is bigger than the naturals. You bet it is. It's got all the other ones. True, true, true. Now, the next one, 7. Some numbers belong to more than one set. It's a statement. True or false? True. True. Absolutely, that's true. Absolutely, it is true. Number 8. What are the 2 main characteristics of irrationals? Okay, so the first one. Can't be put into fractions. Okay, and what else? Yep.
It's a continuous decimal.
It is a run-on decimal, yes. It's a run-on decimal. Okay, and non-perfect squares give us a run-on decimal answer. That's why non-perfect squares are in that category. Now it says, why do we use the letter Q to represent irrationals? It stands for quotient. Good. Okay. It stands for quotient, which means numbers that can be put into fraction form. Okay, that can be put into fractions. Okay, I just wrote the still in number 10. I'll erase it in a moment. I write very large, as you know. So number 9 says quotient has numbers that can be put into fraction form. Okay, if it's a rational number, it definitely can be put into a fraction. Let's look at number 10. Has everybody written that down? I can erase it.
On the way.
Number 10 says, we use Q with a negative sign on top to represent the set of irrational numbers. What does the line on top of Q mean? One word. It means one word. Starts with an N. Not. It means not. Okay, the line on top means not. So not rational. Okay, so it means not. 11. All numbers belong to the set of real numbers. All those numbers all belong in the big box, real numbers. Yes, absolutely true. Yes, they do. Because rationals, irrationals, they all are part of the same system. It's called the real number system. So yes, all of them belong in the box. Okay. What is our smallest set of numbers? Natural. Natural numbers. Which set of numbers includes the positive whole numbers and negative whole numbers and 0? Integers. Okay, quit hollering out, please. Let's raise our hands like proper. 13. How many sets of numbers do not include fractions? Okay, let's take a look at the examples. Does natural include fractions? No. Does whole include fractions? No. Does integers include fractions? No. Does rational include fractions? Yes, this is the only one that includes fractions. But they're all part of the giant system called real. So how many sets of numbers include fractions? 2. Now, so, right. So how many do not? 1, 2, 3, and the irrationals. So 4. So 4, because we've got natural, wholes, integers, and irrationals. All of those cannot have fractions. 15. If a decimal number has a pattern or repeating digits, it's called irrational. Is that true or false? False. That is false, yeah. That's why we call those ones. That's actually the definition of a rational number. Yeah, exactly. Okay. Let's take a look at our number line. Every spot, every number, every digit, unless it's an irrational number, has a number on the number line. Okay? So this one says every number has a spot on the number line except irrational numbers. Okay? Except irrational numbers. How come? Because they're run-on decimals. And run-on decimals can't be put into a fraction. They're rounded decimals.
That would mean you get nowhere. You get to the first number. You get to 0.
What are a couple of characteristics of the number line? We have 0 in the middle. So we have 0 in the middle. We have the negatives, negative numbers on the left, positive numbers on the right. Okay? And the spaces between them, we can actually put the spaces between them. So I can make another number line that looks like this. And I can create one that's got, let's put 0 there, and I'm going to put number 1 there. And I'm going to go, there's 4 notches between. How do I know what that's going to be divided into? How do you figure it out? Is you count how many spaces away from 0 it is. So, 1, 2, 3, 4, 5 spaces away. Okay? So that means that each one of those would be put into a fraction over 5. Okay, does that make sense? That's what we're actually doing. So if I wanted to find that out, this would be 1 over 5, 2 over 5, 3 over 5, 4 over 5, and 1 is 5 over 5. Well, 5 over 5, when you divide them, gives you 1. Okay? So let's say you had a number that was right here on the number line, and you had a 0 here, 5 spaces, and a 1 right here. How do you know what number it is? You count by the spaces like I just showed you. Okay? Those are called, those little ticks we call them, those are the spaces they're divided up into. They're called increments. So you want to count out how many increments. That means what are they counting by? So in this case, since a 5 is on the bottom, from 0 to 1, they're actually counting by 0.2. So if I count 0.2, 0.2, 0.2, 0.2, 0.2, I get to 1. Those 5.2s give me 1. Okay? So that's how we divide up our number lines as well. This one's just showing us all the numbers right up to it. Okay, so this one's just showing us the increments are even in this one. In this number line, it's not showing us any little increments in between the actual digits. It's just showing us all the integers. Okay? This second number line I drew, this is what's showing us increments that are fractions or decimals. So these increment ones, these guys are going to have rational numbers. So we start dealing with rational numbers when we start dealing with increments. Let's take a look at the bottom. This one says, every real number can be put on a number line. Here's a set of numbers that we want you to put onto the number line. What is a strategy we could use? Some of them are fractions, some of them are square roots. How do I find out what the answers could be, where they belong on the number line? How would I know?
Answer them.
Yeah, put them all into decimal form. That is the first point. So, first of all, put all into decimal form. If you put all of them into decimals, then it's easier to find them on the number line. Okay, I'll give you a couple minutes to do that. Push play when you're ready. So to simplify things, I put A, B, C, D, A to I up there. Instead of you having to write all of the numbers on the number line, just place the letters on the number line where they go approximately. If it's a non-perfect square, round it to 2 decimal places. That'll help you find the number on the number line and the spot it goes in. Okay, -3. So A is going to go right there. 0.7. B should go right in there between 0 and 1, but closer to 1. C, -0.5 repeating. It's going to be halfway between 0 and -1, but a little bit closer to -1. So C goes in there. D, 0.4. D is smaller than B, so D goes closer to the 0, because this should give you 0.4. The digit 4, letter E, should be over here. F gives us 2.5, so right in the middle, between 2 and 3, there's F. Then we've got -0.91. So letter G is going to be closer to C. It's going to be on the other side of C, so right in there, that's going to be letter G. Okay, -0.91, not quite at -1. Then we've got letter H. What's root 9? 3, good. So root 9, H goes right on letter 3. And then we've got root 2. Root 2 gives us 1.41. So that one's going to be between 1 and 2, but closer to 1. So right about in there. So that's root 2, which is letter I. All right, check your work and make sure you have that. This concludes lesson 2.1 of real number system and number lines.